Hello, you're with Dave Staublin, and we're doing some good math here. New topic, Introduction to Graph Theory. So here's what I'd like to do first of all. Let's do a little introduction. Say that we had 9 dots arranged as so, and your challenge is to, without lifting your pencil, draw 4 straight lines that intersect all the points. Now, I'll give you a hint here. The hint is think like Taco Bell, outside of the box. Okay? Pause right now and then see if you can connect all of these without lifting your pencil with 4 straight lines only. Okay, we're back. Let's see how you did. Well, I said think outside the box, so this is what I would do. I would start here, go to the diagonal, go down, go this way, and back. There's 4 straight lines. We intersected all the points. We never lifted our pencil. Ha! Pretty cool, eh? Alright, you're going to find this topic in Chapter 3 of your textbook, and this first information comes from Section 3.1, and what we made up here is a graph, and so I'm going to draw another one that we can use as an example. Here are 5 points, and we'll make it look like a house. Okay? So this is called a graph, and it has what are called vertices, and the vertices are what look like dots. So in this case there are 1, 2, 3, 4, 5 vertices, and then these lines that connect them are called edges. Now in this case there are 1, 2, 3, 4, 5, 6, 7, 8 edges. The tricky part is that intersection right there. It looks like an intersection, but it is not a vertex. The vertices are these ones that have dots. This doesn't have a dot, so it's not a vertex. This could mean, like, say that you have a bridge connecting these with a road going underneath. So they cross each other, but they don't intersect. Okay? So here's the thing about graphs. The shape is not important. Only the relationships are important. Shape is not important. Only the relationships. Okay, clean up my writing here. So for example, we could have the same graph and it might look like this. And these two are equivalent to each other. They have a different shape, but they have the same relationships. Okay? Alright, I'm going to slide up here a little bit. Now, there was a famous mathematician who lived in a part of Europe, Prussia, and this was back in the days before televisions, and so for entertainment they might go out for walks in the evening. Now, there was a little town where this mathematician lived, and it was called Königsberg, and it was in Prussia, and there was land on this side. We'll call that land A, and there was land B on this side, and then there was a river that ran through it. Okay, and in this river there was an island B. Whoops, I'm going to call that land D. This is island B, and there was another island C. Okay, and both sides of the city and the islands were connected with bridges. So there's one bridge, there's another. The islands were connected with a bridge, and then there were 4 bridges like this. Okay, and so this scenario could be represented by a graph. where land A is this dot, island B and C are here, and land D is there. So I'm going to label those A, B, C, D. Now, if you look at your graph here, land A is connected to B, and it's connected to C twice. C is connected to D twice, and it's connected to B, and then B is connected to D. And so there is a graph of Königsberg, Prussia. Okay? So the question became, at this point in time for entertainment, is there a way to start at any one of these points and walk across all the bridges without ever traversing one of the bridges twice? Okay? So we can model that either, using this graph. And so why don't you pause the video once, draw a little picture, and see if you can do it. Okay, are you back? Did you figure it out? Here, I'm going to try it with a different color. Say that we started at A, and we went here, and then we went here, and we went there, and back. And now I have a choice. I can either go across this bridge or across this bridge, but I can't travel across one and get to the other without doing one of the bridges twice. So it looks like it's not possible. Okay, let me flip the notes over here a minute. Okay, so let me give you another one. The question is, can you trace all of the paths or all of the edges without lifting your pencil and without going over any edge more than once? And here's a couple different ones you can try. Okay, so pause again and try and see if you can do it. And if you can, look for a pattern, and if you can't, look for a pattern that tells you whether you can do it or not. Okay, I'm going to give this a try. I'm assuming you're back from the pause. I'm going to start here, and I'm going to go boom, 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 and boom. I was able to traverse all the edges without passing any of them twice and without lifting my pencil. And in fact, I started and ended at the same location. Now, I'm going to try it again with this one. I'm going to choose to start up here. Let's see. Maybe I'll start right here. Okay, here we go. I'm going to go across here, 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 and here. Now in this case, I started here and I ended there, but I was able to do it without traversing any edge more than once and without lifting my pencil. So here are some rules and some vocabulary. A graph is connected if it is possible to travel from any vertex